there are some questions here. Firstly, the functionality of device driver. So to answer this question, okay, you need to first know that a device driver is part of the OS kernel, and its functionality is to initialize and release the device, and also it tries for the transferring of the data from the kernel to to and from the hardware. Okay. Then read the data that the application sends the device file, and also return the data request by the application. Finally, okay, it can detect and handle errors in the device. Then the prog system. Okay. So the prog system is a kind of virtual file system created on the fly. And when system boots, then when the system is shut down, okay, so it is dissolved. The prog file system contains useful information for the processes that are currently running, and it is regarded as the control and the information center for the kernel. It can provide communication medium between kernel space and user space. So here, okay, the features of block devices. We know that in Linux, there are three types of devices: character devices, block devices, and the network devices. So they have different features. So for block devices, okay, when comparing with the character devices, okay, the main feature is that it can support random access. So why it is called a block device? Okay, it stores information in fixed size blocks, and each block has its own address. So during I/O, okay, the block devices and write data in buffer to device at one time, or read data from a device at one time and put it into buffer. And each block can read and write independently of other blocks, which means that okay, the I/O for the block devices can be done in parallel. Obviously, it means that several blocks can do the I/O simultaneously. And the disk, our hard disk, is the most common block device. So during I/O, okay, a block device is generally viewed as multiple blocks, while each block size is generally 1024 bytes. But also, okay, in Linux, it allows block devices to be read like character devices, which means that Linux allows any number of bytes to be transferred at one time. Then how to use ins mode and I mode. So here, so when you use ins mode, be aware that you should be with the root privilege. So in Linux, you need to use sudo. Of course, in some version of Linux, the sudo is replaced with another command called su. Su. So anyway, so you need to first use sudo or su to require the root privilege. Okay. So here then, for the name of the kernel module, okay, here speaking, it is with the postfix .ko. Okay. So here, if we want to load a module, Linux kernel module named hello, okay, into the kernel, okay, then we need to use the command sudo insmod hello.ko. So after you input this command and press the character return, the system will ask you for the password of the root user. Okay. Then if you can type in the correct root password, okay, then this command can be executed. Okay, of course, we can check whether the module is successfully installed. Okay. So it depends on whether in the initialization function of this module, you have put something in a log or so. So here, in the example, we discussed in our previous lecture, we output something, like the string, loading hello module, in the module init, or module initialization function. So here, when this module is successfully installed into the kernel, then this string will be written into the kernel log. So we can use the command tail -f to check the tail of the kernel log, because that this string should be just written into the kernel. So it should be at or near the tail of the kernel log, because the other kernel module or core kernel will also written something into the core kernel, into the kernel log. It is dynamically updated. Similarly, to uninstall module, we need to use the command I module. So this I module should also be used with root privilege. But here, we just use the name of the module. No, not like that. Insmod, we need to insmod hello.ko. But here, I module, we need just its name, hello, and that's it. Similarly, if we have put something if we output something, for instance, the string, like the unloading hello module, to the kernel log within the release function of the module, then once the module is successfully uninstalled, such string should be written into the kernel log. So here, if you, in this example, so once the module is uninstalled, then we can see the string here. Then what is the kernel symbol table? So kernel symbol table, it contains global symbols, such as global variables and global functions in the kernel. So the so-called symbol, it just refers to the variables and the functions. Of course, when you load a new kernel module into the kernel, then the kernel symbol table will be updated, because that your kernel may provide new symbols to the kernel. Okay. For instance, you may define a new global variable or define a new kernel functions. Anyway, so if you want to check the current kernel symbol table, then you can use the command /proc /key or symbols. Because that the /proc this file system contains kernel information, such as processes, kernel symbols, and so on. So here we can use the key or symbols to check it. Then why we need the mode probe command? Because that we already discussed that we can use the ins module, this command to install kernel modules. But sometimes the one kernel module may depends on another module. So that the loading sequence of the modules should be arranged based on the dependency between the kernel modules. But if you just use install ins module, it is very possible that you wrongly load a module which need another. For instance, you load a module A, but it actually depends on another module, say B, so that you need to first load kernel module B, and then you can have the kernel module A. So here, we can to handle this problem, we can use the mode probe, because that its functionality is similar to the ins mode, but it can once it load obviously install a kernel module, it will also automatically load other modules that are required by the module you want to load. So that with this module probe command, we will not will make any mistake on the loading sequence of the kernel module. Also, one mode probe command can sometimes replace several ins mode commands. Finally, how to use auto tools to generate a makefile. So the auto tools is a tool provided by Linux kernel to automatically generate a makefile. Because that for a complex project, written a makefile by human is also tedious and error prone. So there are several steps. So firstly, you need to run the auto scan. So it checks the source files in a given directory and also in the subdirectories, and creates the config for the scan. Here, the config.scan is a prototype of the config.in, while the config.in will be used by the autocount. Here is the example of the config.scan. So the macros within it, we already discussed in the class. So I just quickly go over it. We need to run the sa local. So this command is to generate a file name named sa local m4. So this one is used to handle the micro definitions. Then we need to run the AutoConf to generate config this script. So we know that to install a tool from the source code, generally speaking, we need to first run the config script. Then we can use make and make install. The config is to create the makefile corresponding to the current environment. Then we run auto head. This one can generate the config.h.in. The fifth step, we run auto make. So this script file, used by the auto make, is the makefile.am. While the makefile am, we need to provide it by our own. So here, this is the example of the makefile. So including the auto make option, bin programs, and the source programs. So this is the executable in programs, while hello source is how to generate which source files are needed to generate this executable. Then you use automake to generate the config.in. Finally, we can run the config. This one will convert the makefile.in to makefile. So actually, when you use the config to generate the makefile, it actually leverage the auto tools provided by Linux. So, but actually, during the process to generate the makefile, some intermediate file, for instance, the makefile.ama and also the config.in, all these things are already provided by the author of the project. So, generally speaking, when you download some source file from the website and try to install it to your own Linux system, you just need to run the configure, then run make, then run make install, and that's it. Of course, this is a common usage. For some more detailed usage, or for specific installation of a certain software, it's better to read its document first. So you might need to prepare some, for instance, libraries or set some environmental variables and so on. Okay. Then we come to let's move on to today's new content. Okay, so in our previous lecture, okay, we discussed the development of the kernel module. Okay, so here is the example of the kernel module source code. Okay, so in it, we provide a self-defined function, myPrint. So here, once this module is loaded into the kernel, then in the kernel symbol table, there you can find the myPrint in the kernel symbol table. Then in the initialization function and also the release function of the kernel module, we use myPrint to output a string loading hello module or the unloading hello module during the installation of the module or uninstallation of the module. Then the module init and the module exit is used to register the hello load and hello unload. These two functions as the initialization function and the release function of the module. So that once this function will be invoked during installation, while this function will be used after the once the module is uninstalled. And this string will be written into the kernel log. Then this is the makefile. Okay, let's have a 5 minutes rest. Okay, please come back. Okay, please come back. So, okay, this is the makefile. Okay, for this for this kernel module. Okay. Just speaking, okay, we should be aware about how to use the macros here. Okay. The key version, the PWD. Okay. Just speaking, it actually just do a replacement. Okay, then for ins mode, okay, we know that it is used to install the kernel module. Okay. But actually, the ins mode, okay, within it, okay, ins mode itself, okay, is a function of the kernel. So it actually uses the sys create module, okay, this kernel function to allocate memories for the loaded module. Okay. Then use the get kernel symbols, okay, to access the kernel symbol table. Then it uses sys in the module to copy the relocatable target code into the kernel space and calls the initialization function of the module. So we can use the /proc modules, okay, to check whether your kernel module, okay, is installed successfully. For instance, here, okay, we can say the hello. Okay, so it means that the kernel module hello is loaded into the module, is loaded into kernel. And also, okay, you can say that okay, through the /proc /k all symbols, okay, we say that the myPrint, okay, this function is a global function, so is already added into the kernel symbol table. Okay, let's continue to discuss the Linux device driver. So we know that in Linux, the device driver can be categorized into kernel device, block devices, and also the network devices. So most devices belongs to the kernel device and block devices. While the usage, obviously the development for these two types of device driver is similar. So here I use the kernel device as an example to discuss it. So here, let's see how the correct device drivers exist in Linux kernel. So firstly, in Linux kernel, there exists an array named character device. So it is short for the correct devices. This is a macro. So it is the maximum number of correct devices in the kernel. Then we say that this array is of the type device struct. So this is a data structure of the device struct. So it contains two fields. One is the name. So actually we know that this is a constant char point, so it is actually a string. Then the FOPS, the file operations. So this is actually another structure. We see that this is the data structure of the file operations. It has the struct module star owner. So this is a pointer to the module itself. Then is a bunch of the function pointers. So all these function pointers actually we see that in LC, read, write, read, and so on. Okay, all these things are actually similar to the operations of a file, right? Okay. So actually, remember that in Linux kernel we treat the device drivers as normal file. Okay. Then we can apply the file operations on it. So here, we can use the corresponding file operation, obviously file operation system calls to it. But actually, these file operations are actually overriding. We use it overriding. So if you actually want to use some file operations, for instance, read or write to it, okay, so you can provide your own version of read, your own version of write, and so on. Okay. So you actually you need to override the needed operations to this device driver. Then we know that the carry device is array. Okay, it's an array. Okay. Then each index within the array is actually a device number. Well, each element of this array describes the device driver of a device. Then we know that each element of the array device has a field name and FOPS. Then the FOPS actually corresponding to the file operations is a bunch of file operations. So we can override and implement the needed file operations for this device driver. Then to register device, when system booting or module loading, the device must be registered into the corresponding device array. So here the kernel use the function register carry dv. And this function is prototyped like that. It will returns the major device number. We can see that the 3 parameters, the major number, the module name, and also its related operations. So so you see that this is actually the index to the carry dv. Then this is is actually the content of the element of the array element. So actually is that within this register carry dv, it is actually write this content to the corresponding slot in the array. Similarly, unregistered dv. So when the operating system is shut down, all module unloading. So we need to unregister devices. So the corresponding kernel function is unregistered character DV. So this is to remove this element from the carry DV array. Well, why it is used an array? Okay, because that generally speaking, a device is relatively stable. Okay, generally speaking, we do not load and unload a certain device driver. Okay, frequently. I will load or unload a kernel module frequently. So this array is relatively stable. Okay. So to access the device drivers, obviously kernel modules within the carry DEV more quickly. Okay. So the kernel organize them as an array, not a linked list. Okay. Although to add something to an array and remove something from an array, we know that we need to adjust the array. Adjusting to the array a little bit will incur some overhead. Incur more overhead than the linked list. But the access speed is much more faster than the linked list. Okay, so for the operation functions, so we say that from a data structure, it provides many function pointers so that we can override them. So when OS invokes the corresponding system calls, it will use the implementation in the driver to realize the concrete operation. So for a certain device, the function that is corresponding to a system call is fixed. So here is all the possible driver operation functions here. So actually, in the usage is similar to the final operation. So for seek, it is used to change the current read or write position of an open file. When its return value is a new position. Then the read, here read is to read data from a device. The return value is the number of bytes read from the device. Then the write is to write data to device. While the return value is the number of bytes wrote to the device. VDR, just speaking, we know that in the final operation, the directory is also considered as a regular file. But here, just speaking, we do not consider the device driver always as the device as a directory. So just speaking, this function pointer should be none normal. Well, select. So this one is to ask if the device is readable and writable, or if an exception condition has occurred. Well, IO-CTL. This function is to manage I/O channel of the device and control some characteristics of the device, such as the baud rate of the serial port, the speed of the motor, and so on. And map here is to map the device memory to process memory. Open. The open is always the first operation on the device. So open the device and allocate the needed resources. The driver operation functions release. This one is to is used when the device is shut down or we say removed from a kernel. Here speaking, it is the last driver operating function to be used. So it will release the resources allocated by the open and then shut down the device. But I think this function is to write data in a buffer to the disk so that the content of the file on disk is the same as that of the file in the memory. Well, I think this is a little bit different from the fsync. Okay. So for this function, okay, so when the system calls this signal function, the signal function will mix a signal correspond to a function, and the corresponding function will be called whenever the signals you receive. So it means that only when the corresponding handler receives the predefined signal, then the content of the, for instance, the file, okay, or content read from the device or content from memory, okay, will be written. Then the check media change. So this one is used only for the block devices, okay, like the hard disk. So for this function, okay, the kernel calls it to determine whether the physical media in the device has changed since the last operation. So if it changed, okay, it will return 1, or not, it will return 0. Then revalidate. Okay, this function is used when the disk state changes. It initializes the device. But although okay, I just described the functionalities of all these functions, okay, but actually, okay, we will not register so many operating functions in a device file. Okay. Generally speaking, we just use some of them, okay, or we say implement, or we say the override some of them. So for instance, here, okay, in this example, okay, we just override the read, open, and release. Okay. So this is these three things, generally speaking, is normally overriding. Okay. So to override them, okay, we need to provide the corresponding implementation read, device read, device open, and device release. Okay. So this is the function, okay, written by our own or written by the device drivers also. Okay. Well, for other file operations, okay, simply provide them with the none. Okay. So null is with null is empty. Okay. So with the null pointer, okay, then for these file operations, we cannot apply it to this device file. So here means that for this device file, we can only use the read, open, and release. These three file operations. Of course, written so many null, okay, is not is tedious and error prone. Okay, for instance, you may miss one line of null. Okay, then you will get some error. Okay. So for instance, suppose okay, the third row, okay, so the null behind just below the device read, okay, is removed, is somehow you missed it. Okay. Then the device open is actually not provided to the open. Okay. While the release is actually provided to the open. So be aware about that. Okay. So that we can use another format of registration of the file operation function like that. Yeah. Dot read, okay, device underscore read. Dot open, device open. Dot release, device release. So here we simply register these three overriding function, okay, to the three function pointer. So that we don't have to write so many nulls, and we may get some error, okay, because of missing something. Okay. We can use this format to register the overriding file operation functions for this device file. Okay, then let me introduce one special kind of kernel device file, which is called the watchdog. Watchdog, this device driver is widely used in the embedded system. So we know that the embedded system sometimes needs to be used in some harsh environment and used with relatively long time without maintenance. So it is very possible that there are some system error happen. It may got something wrong due to some external interference. Okay, so for instance, someone hit it, or it somehow disrupted by some, for instance, something like for instance, EMP. Okay, anyway, okay, so all these things may cause system error or system shutdown. Okay. Anyway, okay, if the system has something wrong, okay, we need to manage to recover the system, right? Okay. But to recover it, okay, we need to somehow reset the entire system. So this is the usage of the watchdog. Okay. So when the system gets something wrong, or it runs out, okay, we use this watchdog to recover it. So why it's called watchdog? Okay, this one will continuously runs within the system and watch the current status of the system to see whether it is running out. If it is running out, the watchdog will be used to recover it. Okay, and say the watchdog. Okay, just speaking, how to recover a system for embedded system. Okay, we know that embedded system is really simple. Okay, usually it is executed some tasks within a loop. Okay. So this is called the cycle of the system. Okay. So for instance, maybe one cycle of the system is 1 minute or so on. Okay. So after 1 minute, this system should perform the tasks from the beginning. Okay. So here, suppose the system gets something wrong. It means that after 1 minute of running, the system did not come back from the first task. Then it continues to do something else. Then here, when you say this system runs out, and it should be recovered by the watchdog. So here, suppose that the time of one cycle of the system is TP. Then to watch it, because the cycle of the system is TP, then of course, okay, only when the system runs out, okay, so means that it actually runs longer than the TP without without rollback, okay, then we say that it runs out. So that we need to set up the time period of watchdog Ti, okay, and this Ti should be greater than the TP, okay, but not too much greater than, okay, just being near the Ti and near the TP, okay, just larger than the TP. Okay. So after the system program runs for one cycle, the count value of the timer is modified. So as long as the program runs normally, the timer should not overflow. But as I just mentioned, because the embedded system usually runs in some harsh environment, or it may be get some external interference. So the timer may get something wrong and overflow the predefined time cycle. So in this case, due to the interference or system error, the system cannot modify the count value at the TP. So in this case, the timer will overflow. Then will cause a system reset. This the watchdog will cause a system reset. So here inside the watchdog, you can say that the system ran out of the TP. So time overflow. Then when the timer reach the TI, so it actually overflows the TP. Then in this case, the watchdog should take action and cause a system reset for the entire system. So here, this watchdog we will use this example watchdog. We will use the open, release, and write this three file operations. So let's take a look at the example. So here, is the watchdog open. So we say that within the function, the pointer k, watchdog device will be open. So this one will also be written into the kernel log. Then here, if watchdog DEV, so this will returns negative E busy. So this one means that it will check if any other guy already used the watchdog. So we say that this if only if the watchdog is watchdog DEV is greater than 0, then it will return is minus E busy. So this is a macro. It says that this device is busy. It will return this error information. Well, if this watchdog DEV is 0, this means that this watchdog device file will not be used by any guy. And we say that watchdog DEV plus. So this is plus the value by 1. Then also the mode in this micro, mode NZ use count. So this is the micro to indicate that this module is used. So this is this to increase the counter of usage of this module by 1. This is the usage of this micro. Then we say the following this is the two statement to initialize the watchdog. So here the WT CNT this one is actually corresponding to the TI. when the system runs out of obviously the cycle of the system has only one, and the system continues to run. When it reaches the WT CNT, this counter, the watchdog will be triggered and reset the system. While the WT CON, this one is used to set the enable or unable this watchdog. Then watchdog release. So here, let's see. This it use the micro module DEC use count. So this is to decrease the usage counter of this module by 1. Then module in use. Here the module in use is actually a micro to check the usage counter of this module. So if it is 0, here we said only when the counter here is 0, then this condition will be true. Then the WT CON is set to 0. That means that we disable the watchdog. While here, when in the watchdog open, so here we actually enable. This is actually to enable the watchdog device file. While here, because that we say there's no one use this watchdog device file. So here we set the WT CON to disable the watchdog. For the watchdog device, if the user open it, the counter register must be reassigned before it is decremented to 0. So here we need to provide the watchdog right this one to reassign. So here we actually use one kernel function called the copy from a user. So this one is actually a buffer. Buffer is from the source. While this one WT CNT, well, this is a destination. So means that we copy this number of bytes content through the buffer to this place. Then this one will be used to reassign the counter register WT CNT. Because that we need to also reassign this counter register during the cycle of the watchdog. Then here, let's see. In the watchdog init, so this is the initialization function of the watchdog module. So we say that we register this watchdog into the character DEV. So we register watchdog as a character device, and with the name, with the device number, the name, the name here is the micro, the watchdog, the device number, the 234, and also the corresponding watchdog file operations registers. So here, if the register character DEV returns a negative value, then it means that it fails to register the watchdog device driver into the carry DEV array. Okay. So it might be that there already exists a watchdog device with the same name or with the same device name. So this is a possible reason. In our case, we will output an error message in the log. Then, for the release function of the watchdog device driver, so here we simply unregister this watchdog device with the unregistered carry DEV function with the device number and the device name. So here, also, if the unregistered carry DEV returns a negative value, then it means that we cannot register unregister it. It is possible. The reason is possible that the possible reason is that the watchdog device driver is not does not exist in the carry DEV array. Then the module init, watchdog init, module exit, watchdog exit. These two is to register watchdog init as the initialization function of the watchdog. Now this one is to register the watchdog exit as a release function of the watchdog. Then here, let's say the main function of the watchdog, how to use it. So in the main function, this is this is the user level, a user level application. Let's take a look. So here we use the library pthread. Do you know pthread? Or have you learned multi-thread programming? Do you know the multi-thread programming? It's not. Anyway, so pthread, is a multi-thread libraries in the Linux, but for the user application. So here, we declare this thread variable, watchdog thread, and return value, the ch. So firstly, we open the watchdog device. We see here, this is the place where the watchdog is installed. So it is similar to use the open system call to open a normal file. Also the path and also with the model with the mode to open this file. So this one is to open it with the read and write and the non-block. So means that this one is open it with the characterized I/O, not the block I/O. Then here, why we need a thread? It is because that this main function is actually refers to the embedded systems task. So here we said there's a while one, right? So actually this one within this loop, it is refers to the task of the embedded system. So this one will loop forever. But this there might be something wrong, okay, so that the timer will be overflowed, which should be adjusted or reset by the watchdog. So to watch this while loop, or we say to watch this task, okay, the common way, okay, is to create a thread, okay. Here we create a thread for the watchdog. So we say here p thread create, okay, with the watchdog TLD, okay, this watchdog, this thread value, okay, then the feed dog thread. So this means that we create a thread, new thread for the watchdog. Be aware that here when we run the this program, okay, this min, okay, is already being a thread, okay. Then here we create a new thread, okay, but these two threads within the same process. Okay. That's why we need a multi-thread program, because when we compile a program, okay, like min or something, okay, and run it, okay, it will launch a process, and with the min thread, okay, while the min thread's entry point is this min here, min function here. So to watch whether this thread, okay, is overflowed or has something wrong, okay, we need to also create a watchdog thread to watch it. So that's why we use the p thread libraries, okay, and create a thread, okay. Then with thread entry point function, okay, feed dog thread. Well, okay, normally, okay, when we directly run this program, okay, the system will create a thread, okay, with this min function as the entry point function, as the entry point thread function. Okay. Then we say, okay, here the feed dog thread, okay, this one, okay, is also a while loop, okay. Here we see some value, okay, feed dog value, return value, okay. So here, yeah, we say that this one, okay, we print f, okay, feed dog, okay. So this one is to show that, okay, the watchdog thread is actually running. Then here we say write watchdog fe, okay, watchdog value size of int. Okay. So essentially, okay, remember that what is the write, okay. When we call a system call write, it will invoke the watchdog write, and actually it will write the buffer to the WT_CNT. Okay. So here the thread is actually reset the WT_CNT, okay, every 20 seconds. This every 20 seconds is implemented by the sleep. Okay. We know that the sleep here is sleep something, okay, you have to sleep for several seconds, okay, by the number. Okay. So here by you invoke the write system call, we actually write the feed dog value, okay, to a WT_CNT. Okay. So actually, okay, in the idea of this program is that here this while one is the main task of the embedded system. Then to watch whether this main task has been found wrong, okay, we create a new thread, okay, with the watchdog device here. Then we periodically check whether there is something wrong. If not, if there is okay, okay, there is okay, we will just reset the counter of the building watchdog. Okay. Of course, okay, this one is a little bit difficult, okay, but don't too much worry about it. Okay, time is up. We stop here today. Okay, so in this Friday, okay, we still have a class, okay, but it is an experiment. I will send you the experiment guidance before the experiment.
Okay.
So this is in this Friday, okay, we will have an experiment.
Okay. When is the exact date for the final exam?
It will be on the 18th week.
Which week are we now? 16 or 17?
18th week.
Yeah, but this week, is it 16 or 17?
This week is 15th week.
Oh, so we have 3 weeks from now.
You still have 2 more weeks. Okay, see you on Friday. Bye bye.
See you.
Okay, so.